floor is yours. Thank you. Okay, so today I'm going to speak about this disk test to study the hydrogen embrittlement. All my co-authors, but despite the fact that there are many people, it's just the starting of the project. Okay, so maybe you don't know this disk test. It's actually a standard, ISO 11114-4. Let me find the pointer. No? No, okay. So I will move to the screen. So here, this dark shape here is actually the disk. And on one side, it's pressurized with the hydrogen. On the other side, it's just free, sitting in the air. And the disk is clamped here. So it doesn't move. It's rather thin. The thickness is 0.75 millimeters. When you do this test, very often, what you observe is that failure occurs right in the clamping area, which is really a problem if you want to make mechanical analysis of the problem, because obviously in these regions, stresses are very complex, and depending on the clamping condition, the stress may vary from one test to another. So we decided to redesign this disk geometry with the constraint that we shouldn't change the setup. We use the same setup, but we can modify the test specimen. And I'm also going to simulate these experiments, accounting for the interaction with the hydrogen. Okay, so here are two geometries that we proposed. So the first one, many dimensions are fixed by the setup. We decided to use a maximum thickness of 3 millimeters. And at the center, you have a zone which is flat and has a thickness of 0.75 millimeters, which exactly corresponds to what the standard is recommending. And here, we could optimize this geometry with respect to the inner diameter r and this radius of curvature ρ. The second test is somehow different. We have a notch. Once again, the minimum thickness is 0.75. Here, the thickness is 2 millimeters. It's enough. And we just have to optimize the position of this notch with respect to the axis of symmetry here. And so there is only one parameter to optimize, which is r prime. And indeed, we have been optimizing that using a FE simulation, assuming pure elastoplastic behavior. And we took the behavior of a X52 line pipe steel. Here are the boundary conditions. So we have pressure on the inside, no pressure outside. It's clamped on both sides. And here we need to model the contact in the zone where you have clamping. So here are the results we got after optimization. So here's the simulation of the initial design. So you see that plastic strain is very localized in the clamping area, and nothing much happens here. A little bit of plastic deformation, but it's way smaller than the deformation you get in the clamping zone. If you have a look at the, okay, it's working now. The cup specimen, there's a little problem with the design and also with the initial design. It's because of the loading, you have a bending on a membrane stress. So because of this effect, you always get a larger plastic deformation on the side which is not pressurized. So in absence of hydrogen, for sure failure will occur on this side, which is not pressurized, but we don't care. The question is, what happens if you have hydrogen inside? Will it break from the inside because of hydrogen embrittlement, or will it break from the other side, which is not that interesting? This problem is solved with a notch specimen because we have a high concentration of plastic strain on the pressurized side. The only drawback of this specimen is that the volume of material which is stressed is very small compared to this one where you have the central area which is more or less evenly stressed. We did some preliminary experiment with the design, and here are the fracture the crack on the surface of the specimen when the specimen leaked. So under hydrogen, you see this crack on the pressurized side, but you see also secondary cracks, which is a good sign that fracture was initiated on the pressurized side. So we're happy with that. And that's what you get under helium pressure, just a main crack, and that's it. And that's pure ductile failure. So we think that the design is working, and we are going to use it extensively to test hydrogen embrittlement with better condition, better loading condition, so that the analysis is much easier. And then we started the modeling of this test. I guess all these equations, most of you must know them. So I'm not going into the details. So we really have a very simple, or not very basic or very usual simulation using the Sofronis-McMeeking model modified by or corrected by Crom. That's fairly old. In red, I really outlined the coupling terms between diffusion and mechanical loading. As was already shown, pressure gradient influences the hydrogen or lattice hydrogen transfer. We have a coupling because the trap density is linked to the plastic deformation, and possibly the flow stress is also affected by the concentration of hydrogen, so that you get some kind of softening because more hydrogen is present in the material. Boundary condition, so we apply a boundary condition on the pressurized side by imposing the lattice concentration following the Sievert's law, where P is a function of time because we gradually increase the pressure. So what is a little bit more new in this presentation is the way we implemented this model. So we started to, indeed, we have a finite element implementation. We use finite strain. It's obviously necessary if you see the deformation of the disk. But the implementation is based on a mixed element using displacement, pressure, and volume variation. These elements were developed to better control pressure fields in regions which are highly deformed, high plastic strain, and to control volumic locking. Here is an example of the pressure field at Gauss point, not smooth at nodes, at Gauss point, using the standard U-based elements, finite elements, and you see this checkboard pattern, and that's caused to locking. And obviously, if you have a field like that, it's going to be difficult to compute any gradient. Using the three-field formulation, you get a much more smoother pressure field. That's another example, which in this time is really related to the problem. That's the contact in the clamping area that we saw before. And what you see that with the standard elements, you get, again, this checkboard pattern under the contact, which almost completely disappears with these special elements. In the framework of hydrogen diffusion, the main advantage of using this element is that since the pressure is known at nodes, you can straightforwardly compute its gradient that enters the diffusion equation. And that's what we have done. I will not go into the detail of the implementation. The only thing we have to do for hydrogen diffusion, we add another nodal variable, which is the lattice concentration. This is strongly coupled. That means we do not have a staggered scheme. We solve everything at the same time, mechanics and diffusion at the same time. So strong coupling, and we use a fully implicit scheme with a large strain implementation. And here are the boundary conditions for the test I was presenting. So one side, the lattice concentration is fixed. On the other side, the lattice concentration is 0. So that's the first attempt. And indeed, the flux is 0 on both other sides. We use this softening function, which was introduced by Anne and Sofronis some time ago. All other parameters are taken from the literature. And when you start in this business, looking at the big literature, you say, OK, which one I'm going to choose? So, because sometimes, looking, for instance, at the diffusion coefficient, you have one order of magnitude. So what I'm going to choose, I don't know. OK, so here's the simulation of the disk. So that's the initial stage. No hydrogen in the material. And then I'm going to pressurize. So here you see the map of total, I think it's the total hydrogen concentration here. Here you have the plastic strain at a point which is just in the middle here. And these curves, they represent the total concentration, trapped concentration, and lattice concentration. And here we go. So you see that the disk is deformed, concentrations increase, and indeed they increase because here we have plastic strain and a lot of hydrogen trapping. On the other hand, you see that the lattice concentration appears to be more or less stable. And that's it. So on this graph, because we want to know when the disk breaks, what you have here is the imposed pressure on the deflection. Once again, there is no damage in this simulation. Nonetheless, you get fracture because when you increase the pressure, at some point you reach the limit load. Limit load, the thing will explode. And the black curve here is what you get without hydrogen, so just a regular test. And all these curves are what you get with hydrogen. So you see that there is a reduction. So pressure at failure is decreased. And the reason why is just because of the softening. So there is no embrittlement. It's just due to the softening of the steel by hydrogen in the lattice and trapped hydrogen. And you have different curves for different pressurization rates. And if that's fast pressurization rate on the slow one on the other side. So if it's slow, you get more time for the hydrogen to get into the steel, and so you get more softening and it fails a little bit earlier. Obviously, these are just trends, and I don't expect the experiment to look like that. I expect the overall behavior not to be much affected and failure to occur earlier, very close to the black curve. These are, once again, are preliminary results. Okay, so what I've presented is a computational framework for a strong coupling between mechanical loading and hydrogen diffusion. We have developed a specific four-field element. And very soon we'll have the experiment, so we'll be able to better fit the material coefficient. And indeed, I expect the material to break with damage, so we are going to link that with a non-local Gerson model, void growth and so on, and be able to propagate cracks with remeshing and mixing all together. And that's the end of the presentation.
Thank you.